All right, so here I have a problem for you to try. Radical x times cosine of x dx. We're taking the integral from 0 to pi over 2 using the trapezoidal rule with n equals 4. Okay, so go ahead and try that one. Write it out. Okay, write out what you're finding. And then I'll also illustrate how to do this one with the calculator so you can see that one more time. So first of all, let's set this up by hand and then we'll use the calculator, alright? You guys should be able to do both by hand or with calculator. If I ask you to do it by hand, I'm not going to give you things like sine of pi over 8 or something like that, but nevertheless, you should be able to set it all up and make it look how it needs to, okay? So, first of all, we need that b minus a over n. So that's going to be the pi over 2 minus 0 over 4, which comes out to pi over 8. Okay? So, that tells me two things. First of all, that tells me that on the outside of my parentheses, I'm going to have a pi over 2 times 8, so pi over 16. And then on the inside, I'm going to be taking the function, first of all at 0, and then plus 2 times f of pi over 8, plus 2 times f of 2 pi over 8, which is pi over 4, plus 2 times f of 3 pi over 8, and then the last one is 4 pi over 8, which is pi over 2. That's the other end, that's my upper bound, so I'm going to stop right there. Okay? So that's how this would be set up, and the function, of course, is this radical x times cosine of x. Okay, so at this point, guys, we are ready to use the calculator. Alright, so
Oh, wait, I didn't multiply it. Hold on.
So let's enter a video here so you guys can see this and you can refer back to it later if you need. Alright, so here I'm going to start out by first of all putting in the different x values into my list. So I'm going to go to Stat, Edit, and in list 1, I'm going to put in 0. I'm going to put in a pi over 8, pi over 4. Whoop, what happened to there? Second pi. Hang on. Over 4. No. Yeah, pi over 4. And then I need a 3 pi over 8, and then a 4 pi over 8, which is a pi over 2. And that's the last one, okay? So that is now saved in my list 1. I'm going to quit out of here. Now, this one's a little bit different because we don't just have a single place where x is plugged in. But the nice thing with this is that anywhere you see an x, you can just put list 1. So I'm going to put the square root of list 1. That will square root everything in list 1 times the cosine of list 1. That will take the cosine of each of those things. When I multiply this together, it's going to create a new list that has all the values of the function in it. Okay, so there's my new list.
Yeah.
All right?
And then you're going to add them up and multiply by pi over 16.
Close. So what do we have to do before we add them up?
Store.
We could store it or we could just keep it here, but what do we have to do?
Multiply by 1, 2, 2, 2, 2, 1.
Exactly. Okay, so if I go back to Stat Edit, I need a list that has 1, 2, 2, 2, 1 in it. Okay, if you want to store your previous answer as a list and put this as list 3, it's fine. I'm not going to bother doing that because here, what I'm going to do is I'm just going to hit times, and it takes that previous answer. And I have my 12221 stored in list 2. So I do answer times list 2. I hit enter. And there is what you would see if you were doing this all by hand. That's what you would have written in your parentheses. 0 plus 1.1579 plus 1.2533 and so on. So what do I need to do with all those numbers?
Multiply by pi was 15, or add them up.
I need to add them all up, okay? So right here above stat you see list. So second list, we go over to math, and number 5 is the sum. So I do the sum of the previous answer. Second negative sign is answer.
Is equal to 3.2
3.241956 and so on.
and 0.
Now I multiply that. Okay, so what I have at this point is pi over 16 times a 3.24192 or 3.242. Now I multiply that by a pi divided by 16, and I get, rounded to 3 decimals as always, 0.637. Okay, so that is our approximation with the trapezoid rule up to 4 trapezoids. Okay, again, if you need to see that on the calculator again, this will be on the video and you can just go back and watch as many times as you need. So at this point, guys, I want to shift gears a little bit. There's one other review element, and then we want to take a more in-depth look at the natural log function, okay? We're actually going to look at a different definition of the natural log function that we're going to get to here, okay? So here it says for x is greater than 0, create a slope field for dy dx equals 1 over x, okay? Now, this is a lot simpler than it seems because notice dy dx only has an x in it. So that means all of our columns are going to be identical because no matter what y is, that y does not impact our slope. All right, so that's kind of nice. So I'm going to draw just the first and fourth quadrants because it said for x greater than 0. And I'll put x equals 1, 2, 3, 4 here. Okay? So let's come up with a slope field. When x is 1, the slope is 1. Okay, so if I were doing this, here's a slope of about 1. And it would look that way for all of these. Okay? By the way, all of you should be able to do this if asked. Okay? Now, when x is 2, what's our slope? A half. Okay? So a half is a little flatter like that. How about when x is 3?
1/3.
It's a third, so it's even flatter. And you guys are getting the idea here. When it's 4,
I guess it's 1/4.
it's 1/4, so it's even flatter. What's going to happen as x gets bigger and bigger?
It's gonna level off.
It's going to level off. It's going to approach a slope of 0. Okay? Now, what if x was a half?
2.
It would get bigger.
1 over a half, it would get bigger. It'd be 2. Okay? So it's getting like this. Okay? And if we were at 1/3,
Would get
the slope would be 3. Yeah, so what do you notice is going to happen as we get closer to 0?
gonna get
Approaches
1.
undefined.
Yeah, it's approaching being vertical, okay? So if I were to graph this and put the point 1, 0 on here, what is this going to look like?
Like that. I'm just letting.
Oh, the original function was saying?
Yeah, what would the original function look like if we were trying to,
Like that.
like a line like that?
I mean, it
No,
would be
Like curved?
cube root of something.
Okay.
Oh,
We're
wait,
getting
it would go
there,
like- it would go like-
Yeah, it's going to go like this,
Yeah,
okay?
make it curved.
It, as we approach 0, what's happening?
We're gonna approach infinity.
Okay, it's going to go down like that, like an asymptote at 0. And as we go like this, it's going to look like that. Now, what function is that? Do you guys
Cube
know?
root.
Square root. Hyperbola.
Not
Logarithmic.
cube root.
Hyperbola.
A lot.
It's actually the natural log function.
Oh right, we're.
Too far.
That's why the name of the lesson
square
is.
root.
That's why the name of our lesson is natural logs. That's okay. All right, but hey, that's what the slope field would look like. Okay, that's what the slope field would look like. And if you remember, what was the derivative of ln of x?
ln of x.
No, derivative e to the x was e to the x. Derivative ln of x is
Log.
A 1
That
over-
one.
1 over x. Okay, derivative of ln of x is 1 over x. All right, so let's look through here a couple of things, and I want to tie this together. All right, let's not do that. Okay, remember our power rule for integrals. What we're building to here is in the next couple days we're going to look at integrals of natural log functions. But our power rule, remember, did not work
If n is negative.
when n was -1, x of -1. So that integral, remember the derivative of ln of x was 1 over x,
Can't go back.
okay? The integral of 1 over x is actually going to be ln of x, okay? We couldn't use this power rule because if we added 1 to -1, we'd be dividing by 0, okay? Can't do that. Now here's another definition of the natural log that I want you to notice. The natural log is the integral from 1 to x of 1 over t dt,
Makes sense.
okay? Well, let's think about what we were just talking about.
Was this equals to 0, right?
If I take the derivative of both sides, what does the right-hand side here look like? We're going to use,
1 over t.
no? When we took the derivative of the integral, what was that?
1 over t.
That was the second, guys, listen, that was the second fundamental theorem of calculus. That's 1 over x. This is the derivative of ln of x, which was 1 over x. All right, if I wanted to prove this here, before I took the derivative, if I just took the integral from 1 to x of 1 over t dt, okay, the integral of 1 over t is ln of absolute value, ln of the absolute value of t, okay? And I'm going to then evaluate that from 1 to x. All right, well, ln of absolute value of x minus ln of 1. ln of 1 is 0. So this is ln of the absolute value of x. So we just kind of showed that that's the case. We can see with the second fundamental theorem of calculus. We can also see by doing the integral with our new rule here, the integral of 1 over t dt is going to be ln of absolute value of t.
Why is
Okay?
natural log is 1, 0?
Because e to the 0 power would give us 1.
Wait, so what's there?
So down here you can see kind of the expansion of the slope field that we had drawn above. When we have this function y equals ln of x, you can see the derivative at each of the points is the reciprocal of the x coordinate. So here at x equals 3, the slope is 1/3. At x equals 4, the slope is 1/4, and so on.
And that's
Okay.
what the log, the graph, right?
And that's for ln of x. Okay? Now, let's review a little bit about our natural log function. Remember that the domain is only good when x is greater than 0. Okay, that's why up above when we did the integral, it had to be the integral of absolute value of x, because x has to be greater than 0. Okay, also notice that the range is all real numbers. Now the function here is continuous, it's increasing, and it's 1-to-1. Okay, the function is continuous, it's always increasing. How do we know it's always increasing? Well, that's because the derivative is always greater than 0. Okay? The derivative of ln of x is 1/x, and if x is always greater than 0, then 1/x will always be greater than 0. So I know that this derivative is greater than 0 as well. Okay? Does that make sense? All right, again, you got to think about the domain of this function. X is greater than 0 will then force 1/x to be greater than 0 always. Also, notice that the graph is concave downward for its entire domain. Why is it concave downward? Because the derivative, the second derivative, the derivative of 1/x, is a negative 1/x squared. Well, again, if x is greater than 0, move this over, if x is greater than 0, then 1/x squared will always be positive, so when I make it negative, it will always end up being negative. Okay, so that's always going to end up being less than 0, which is why this is concave downward everywhere. Okay? No, that's a good question. How can it have a slope field, different variations? This is something I should have put up here. The integral, okay, if we're thinking of this in terms of a rule, the integral of 1/x dx is going to be ln of the absolute value of x plus c. So that's where that slope field, it could have been shifted up or shifted down. We forced it to go through the point 1, 0. Okay? So now let's visit a little bit more, just talking about the graphs of our natural log function and some of the properties, and use those because we need to make sure that we remember these well, because we're going to use this quite a bit when we try to take integrals in order to actually get stuff that we can integrate. Okay, so we already saw the function of ln of x. What happens when we do ln of x minus 2?
It's just to the right.
Down.
It's 2 to the right. Okay, so it's shifted to the right 2. ln of x plus 3. It's gone to the left 3. Okay, how about ln of x plus 3?
Up 3.
That's up 3. Okay. What about ln of 2x?
Wait, compression by 2? No, that makes no sense. 1 over. Stretched by 1/2. Compression by 1/2. Or
Okay.
not compression by 1/2.
It's compressed by a factor of 2, or it's stretched by a factor of 1/2. It's a horizontal shrink, right?
Yeah.
So horizontal compression. Okay.
The week's over.
I like to say to just half its width.
Have a good weekend, Josh.
Okay. So if I have, starting with this one, ln of x minus 1, notice the minus 1, it's just ln of x and then minus 1. So what does that do to our graph? Yeah, this is going to shift the whole thing down 1. And how about the last one, the negative ln of x?
Reflection over the x.
Yeah, it's a reflection over the x-axis. It's multiplying the whole function by a negative, so that's going to shift it or reflect it down across the x-axis. Just a reminder, when you're transforming things, if whatever is happening to the x, that's going to do something to it horizontally. Okay? We're subtracting 2 from the x, adding 3 to the x. We're multiplying the x by a 2. All of those things are horizontal changes. If we had a negative x, that would be a horizontal reflection across the y-axis. Okay? When we're doing something to the entire function, like adding 3 to the whole function, or subtracting 1 from the whole function, or multiplying the whole function by a negative 1, that's going to do something vertically. Okay? Because we're changing the function, which is our y value. Okay? So just keep that in mind. Now, a couple of rules just to remember. Ln of 1 is always 0. Ln of a times b, you can split it up into ln of a times ln of b. Ln of a to the n power, you can bring that exponent out, so it's n times ln of a. And if there's division, you can rewrite it as the subtraction of two different logs. So ln of a over b is ln of a minus ln of b. Okay? So here, we can actually use this to figure out some other logs, even if we only know a couple. Like here we know ln of 2 is 0.6931, ln of 3 is 1.0986. So if I were to rewrite this as ln of 1/4, and then I recognize that 1/4 is 2 to the negative 2 power, since I have an exponent inside my log, I can make this negative 2 times ln of 2. And now I have something I know. Ln of 2 is 0.6931, so it's negative 2 times 0.6931, and that's going to be a negative 1.3862. Okay? So ln of 1/4 is that. And we could do this with a number of different things. Ln of 24. Well, if you recognize 24 as 2 times 2 times 3, I can rewrite this as ln of 2 plus ln of 2 plus ln of 3. I plug in what I know. I have 2 of those ln of 2's. So 2 times that, 0.6931, plus the ln of 3, 1.0986. And I can figure that out. 1.3862 plus 1.0986. And I get 2.4848. Okay? So again, we use these rules, these different properties, as kind of a way to complete a little puzzle. All right? I'm sorry, what?
I thought there's you need 1 with 2 there.
I just made it 2 times that.
Oh, okay.
Yeah. Okay. And then there's a lot that you can do with these. Okay, we've got the 12.
I think it's
Oh wait, no. Sorry, I get what you're saying. There should be 3 ln of 2's there.
Yeah.
Yeah, there we go. Because 12 is 2 times 2 times 3. You know what? Let's do this. There. but what are we missing? Okay, I accidentally did 12 instead of 24, but what are we missing? We're missing the radical 3, right? So this would be to the 1/3 power, which means I could pull the 1/3 out in front of all of those. So 1/3 times that. Okay? So I just take 1/3 times this, 1/3 times all that, and this would be divided by 3. So, what do we get there? That's going to be a 2, wait, that's going to be a 0.8, 2, 6, 2,
It's 0.8282 and then 6 repeating.
8282.
Yeah.
And then 6 repeating. Okay. There we go. ln of 24 we would do similarly, except we'd have 3 ln of 2's. Okay, because 24 is 2 cubed times 3. 8 times 3. Okay, so we could have 3 ln of 2's plus an ln of 3, and that would give us our answer. 3 times 0.6931 plus 1.0986. Okay, so we have 2.0793. Okay, and then you add them together. So 3.1779. And if I add wrong somewhere in there, sorry, but you guys get the idea. Okay? Now, we can also use these rules to expand and contract. Alright? Let's start with C here. We won't do all of these, but how could I rewrite ln of 6x over 5?
ln of 6x minus ln 5.
ln of 6x minus ln of 5. What could I do then?
Then 6 plus then x minus 1 5.
Yeah, I can make the 6 times x into ln of 6 plus ln of x minus ln of 5. Okay? D looks fun. Okay?
You subtract the numerator by the denominator.
Yeah, anything in the numerator is going to be positive, anything in the denominator is going to be negative. So if we split that up that way first, we have ln of x squared plus 3 squared minus ln of x minus ln of x squared plus 1 cube rooted. So I'll put that to the 1/3 power.
Then you can do ln x squared plus 3 plus ln x squared plus 3.
Yeah, we can. Or just make it 2 times
Yeah.
ln of x squared plus 3 minus ln of x minus 1/3 ln of x squared plus 1. Okay? Now, can I do anything with the ln of x squared plus 1?
No.
No. The addition inside doesn't change at all. Okay? It's not gonna, we can't split that up or do anything with that. Okay, so don't go too far with some of these. But hopefully, as you're thinking towards integration, hopefully you're thinking about this and realizing how this might be useful. Because when we're taking integrals, we don't have a product or quotient or chain rule, so there's no way in the world we're going to be able to integrate this. However, if we're able to break it down into, say, 3 separate integrals, where those integrals we're doing ln of something much simpler, then at least we've got kind of a chance of being able to take the integral. Okay? That's where we're headed with this. That's why we're reviewing this briefly here. Okay? Let's try going the other way. Putting these back together. Let's just do this one here. Okay, we have 3/2 times, what would the inside look like?
ln of x squared plus 1 over x plus 1 times x minus 1.
Yeah, okay, those are both subtracted, so they both go in the denominator. And then since that's the 3/2 power,
The whole thing to the
or that's times 3/2, yeah, then that whole thing, ln of x squared plus 1 over x plus 1 x minus 1 would all be to the 3/2 power, or square rooted and cubed. Yes?
Weren't, if you were to break it up first as x squared plus 1 minus x plus 1 times x minus 1, wouldn't you then have to add x plus 1, x minus 1 instead of having the subtraction between them?
What, like right here, addition?
Yes.
Well, these are being multiplied together, but the whole thing is subtracted. So if you had addition here, it would have to be minus both of them.
So it'd have to be, okay.
Minus the product. Yeah. Okay. Alright, so I think you guys are getting the hang of it. These are somewhat familiar. So I don't think we need to do every single one of them. But, okay?